This week's lesson is about neural networks and using them with TensorFlow. TensorFlow is a framework, a Python framework that is able to create deep learning models that can be used for prediction. So first, we're doing machine learning models. These models were required to have data, and in that data, you had to find the features yourself. So you had to perform some sort of feature engineering. With deep learning models, you do not actually have to find the features yourself. The features can be found for you with something called a CNN, a convolutional neural network. So once you have access to this link, you can click on code and then open with GitHub desktop. And this will allow you to clone your code. Once you clone it, you can open it in Visual Studio Code. I have already cloned it. I'm using the same code base that we did in class. I'm just going to delete some of these sets so we can practice together. And some of the comments will also be available in here that you may not find in the cloned repo. So we're going to talk a bit about TensorFlow. I'm going to talk a bit about neural networks. For TensorFlow, their website is tensorflow.org. You can also search this on Google and you can get there. Their website offers many things. You can learn some really advanced concepts. You can see their API and you can search right here for things like all their layers and everything. What we're going to do is we're going to get started with TensorFlow, and we're going to use this code that they give to be able to explain some of these concepts that they use. Um, this website has a lot of features, so if you have time, go to Learn, Introduction. Under TensorFlow, Learn More. And then you can start with the beginner quick start. But what we're dealing with mostly is some of the loading when we're loading images and the vision tab over here. We're trying to do computer vision as well as convolutional neural networks. So some of this might be important if you want to go through it slowly by yourself. Some of this code will be identical to what we have. Some of it might be slightly different because I'm using a different data set. So what is a neural network? There is a folder in here. I have labeled them 027. There are images, and you can go through them to see what they are about. A neural network is an architecture of sorts that includes neurons. So this circle is a neuron, and there are many neurons. This column is known as a layer. So this is the first layer. We have an input layer. Then we have the second layer, which is a hidden layer, also known as the first hidden layer, but this will be the second in total. Then we have the third layer, and then we have the final layer, which is our output layer. And this structure can change very differently depending on the different architecture you're trying to use. The input layer for us is all the images. So the images will start off here. And the nodes specifically refer to exactly the value that you're trying to hold. So for us, this one first neuron will be a pixel value, for example, and we'll have all of the pixel values for that image lined up here at once. And then this will connect to the next layer. So this neuron connects to this one. It also connects to all of the five that are in this layer. And so this is the first hidden layer. It will create some form of probability in connection to that pixel. So with this pixel, when it hits this connection, it can say maybe this pixel has a 0.05% chance of affecting my output. Maybe this one has a 0.06% chance of affecting my output. Maybe this is 0%, maybe it's 0.9%, and so on. So these hidden layers, they have probabilities, and each one hits a certain point, and it creates a path to be able to get the output. So given some sort of input, it will connect different neurons to be able to give you a different output. So this is more like a digital brain of sorts. So this is the neural network architecture. When we get more than three hidden layers, we call that a deep learning network. If it's less than that, it just becomes a shallow network. It does not do very much. So this is the architecture. You can think about this the same way. It works almost samely for all of the bigger models. But the bigger models just have more hidden layers. So that is the neural network architecture. There is the TensorFlow basics code. This code is the same one as when you land on their page. If you were to copy it and paste it, it's absolutely identical. I have only added these two things to install TensorFlow and Matplotlib. I don't even think we use Matplotlib for this one, so we might not even need this. So I'm going to play this one, and then I'm going to play this code. So what this code does specifically is it imports the TensorFlow package. It shortens it as TF because TensorFlow is really long to spell. So you will most likely see this, you're importing something and then you're shortening the name to something smaller. You can use whatever you like. You could have used TEF, for example. However, TF is the T from here and the F from here. So it shortened it as TF and it's using the a package right here. So from TF Keras in datasets is importing a dataset called MNIST. And MNIST is a dataset of numbers, handwritten digits, and these were collected to be able to perform some kind of learning on them. So if you search on Google what MNIST dataset is, inside of images, you'll see it is all of these handwritten images of numbers, and they go from 0 all the way to 9. So you'll have 0, you'll have 1, 2, 3, 4, all the way to 9. And all of these have black background and white text, so they're all very, very similar. Um, However, when you're predicting, you might have different values for your images. However, they all sort of need to be on the same range so that can be predicted correctly. Then we load the data and we get the train data set. We also get the train labels. Then we get the testing data, and then we also get testing labels. We then take the training data and the testing data and we normalize it. So normalization is a process of sort of rescaling the values. Currently, our image pixels range from 0 to 255, and we don't want them to range this much because when you're doing when you're training your model, you're just usually multiplying all of these numbers. And the bigger these numbers are, it can take so much time and so much memory from your computer. We want these numbers to be really, really small. So when you normalize, you're trying to decrease the variance between these values. So it goes from 0 to 255. When you divide this, it makes it 0 to 1. So the values become shrunk, they become smaller. So now the next part is to create our layers. The model itself is a sequential list of layers. That means this is the first layer, this is the input layer, then this is the second layer. Essentially, this will be the third layer, and this will be the fourth layer. In some terms, you may not really count this layer. We'll talk about counting layers later on. Um, the things that you should note are the input shape. MNIST data was trained on 28 pixels by 28 pixels. So this is the 28 columns of the image, and these are the 28 rows of the image, and they are flattened. What flattened means if this was your image, let's say these were 28 values going this way, and then we had 28 values going this way, what it will do is it will just put all of those on one row. So you'll have 255 and then 1, and then the next row comes, it'll be 23, and then 34, and then whatever comes next will just keep coming next like this. So these values will look something like this. Let me comment this and this as well, so that it does not really destroy our code. So this is flattening. It keeps everything in one row. So once we have flattened our input shape, the next part is a dense layer. A dense layer is just a very simple layer that creates the this specific layer. Like it's just a very simple layer for you to use. It has 128 connections and it has an activation function of ReLU. Activation functions are what are used to, let's say, hit these endpoints and create those probabilities themselves. So when you have an activation function, there are so many of them. We have tanh, we have ReLU, we have sigma, we have linear, there's softmax, and what all they do is that they take the value that you have and they push it in a certain direction. So what ReLU does is it takes any value that you have and it either gives it a value of 0 or it gives you the value that it actually was. So if the value is negative, let's say -3, because -3 is less than 0, it will just give you the value of 0. If it's -1, it will still be 0. However, the moment you hit 0 onwards, then it will give you the value of x. So if the value was 0.1, then you will get the value of 0.1, which is x. And H does something different. Sigmoid is specifically for binary classification. So it will either give you a value that is 0, 1, like one or the other. And linear is just linear. The value is just a function. So if of the function of x, they'll give you that value. So 2x, if the x was 0, then the value will be 0. If for 2x is 1, then it'll be 2, and so on. So these are activation functions. Different activation functions can be used for different models. Um, a dropout layer is one that drops out connection. So when you say I want a zero point 0.2 dropout, it means I want to cut off 20% of the connections of the available inside of the neural network. So given this layer, we have 5 specific neurons, and so that means there are 5 connections. That means if this was 100%, one neuron will be 20%. It means randomly choose between these neurons and cut off one connection. And that can help in regularizing your model, especially if your model is really, really heavy or it's not picking up specific types of features. You might want to drop off some connection so that the model can pick up specific features and really emphasize on those features. Finally, we have an output layer. This is a dense layer. It has 10 values and its activation is softmax. So let's go through the activations. An activation of softmax just means that the value will be reduced all the way to 0 unless it is the maximum value. So let's create 10 random values, 0.01, 0.02, 0.03, 0.01, 0.02, 0.03, 0.01. So 1, 2, 3, 4, 5, 6, 7. 8, 9, and I'm just going to make up a random number, so 0 point, let's say 8. So these are 10 values. What softmax does is that it takes the largest value and then it makes it 1. So given this, it will push all of these to 0. This will be 0. This will also be 0. And then the largest value will be 1. So that when you're predicting, it just finds the 1, and this becomes your result. And this 10 is how many classes you have. With MNIST, the numbers go from 0 to 9, so those are 10 values. You should always pay attention to this last part because if you do keep a different number, later on you will face issues. So if I had kept 11 here, I would have issues later on going on with my code. Similarly, if I kept 9, because I have more output values and I'm keeping less. So this is softmax. Okay. And now there's something called compiling. What compiling does is it takes the structure of your model and it compiles it with the different parameters. We're going to optimize it with a function called Adam, and then we're going to use a sparse categorical cross entropy for our loss, and then we're going to use our accuracy as our metric. So metrics, I guess, is the easiest one. Accuracy is just a value measured from 0 to 1, and it describes how accurate your model is. Loss is a small value that describes how low your model has gone if it's descending on gradient descent. And the optimizer Adam is the function that lets you get to this loss. So when we look at our loss function, let's go with a 2D loss function. This is a line. We can say perhaps this is a function of x, y equals x plus 5. That could be an example of this line. And let's say this describes the relationship between all of these blue dots. So we're saying currently it kind of goes through these blue dots well, it describes it well, that it's close enough. But let's say if this line was down here somewhere, would say it is nowhere on those blue dots, means the loss function is not very, very well. What we want to do is we want to ensure that the function is correct or it's really, really close to our data. The loss function is sort of the opposite of when we're trying to have the function. So for example, in mathematics, you actually have the function. Let's change this function. Let's say the function was actually x plus 5. Um, and the function is similar to this. We say y equals x plus 5. So when we're given a value of x, we're trying to find a value of y. If we're given x as 0, we can say y equals to 0 plus 5. So the value will be 5. Similarly, if y was 1, we will say 1 plus 5, which the value is 6. If we're to do it again, let's say the value was 2, this will be 2 plus 5, so the value is 7. So you can see this relationship. Now, the opposite of this is trying to figure out the function. So this time around, rather than being given the function, we're trying to find out the function. So let's say I have a set of values. Let's say I have 1, 2, 3, 4, 5, and I'm trying to figure out what function represents this data. It's very, very simple. I can say that y equals to x. Because if I'm given x as 1, y will be 1. If I'm given x as 2, y will be 2. So what you're trying to do always is that you're given data, you're given all of your images, for example, 255, 0, all of this kind of data. And what you're trying to do is figure out this function that represents all of these images at once so that you can predict from them. And this is a very simple example of it in 2D. However, when you get to more dimensions, it gets very, very confusing. So the only visualizable version of this is in 3D. Our data is actually in more dimensions than 3D, but this is a 3D illustration of what is happening. So you can see that we have a really high point of this. And what we're trying to do is we're trying to minimize this function so that it gets all the way to the lowest part of this graph. So you could say this might be the lowest part of the graph, or this might be the lowest part of the graph. But what you're trying to do is you're trying to use the optimizer to figure out a route that will get you to one of these spots. When you're training, you might be going to different minimas. You might end up here, you might end up here, you might end up almost anywhere. And you'll never really, really know. You just have to keep testing and keep trying and keep looking at your metrics so that you can figure out if you're really at the lowest part. You will not be able to visually see this when you're classifying. This is just like a render, so you can think about it that way. So this is what happens. And then after compiling it, you can also view the structure of your model. To view the structure of your model, you call model.summary. And this will show you the layers of the models, all of these layers at once, their inputs, outputs, and how many parameters are within that model. Next, we do something called fitting. Fitting is a process of training the model. It takes in the training data as well as the training labels. And then it can also take in validation data. This one, we're not doing validation data, we're just training with the training set. And then there's something called epochs. What epochs is how many times I'm going through my data set. So let's say I have 200 images in my training set. What 5 epochs does is I'm going to have 5 rounds of going through my images. So my first round, it will go through those 200 images. The second time, it will go through the same 200 images. It will keep going through those same images over and over until it reaches 5 epochs, which is 5 times. Lastly, we will evaluate on our test data and our test labels. And then lastly, we will check the data to see the metrics themselves. So I'm going to play this. You can see the summary. This is the model. There's a flattened layer, a dense layer, dropout layer, and another dense layer at the end with 10 outputs. It has 100,000 parameters, which are trainable. It has trained. It takes 3 seconds to train. It has gone through all of my images. On epoch 1, it has reached an accuracy of 86.12%, and the loss is 0.47. This is a percentage. However, this is just a value that you're trying to go down. So the value can start off really, really high. You might even start off at like 10 or 100, but you should ensure it goes really, really low. So it went from 0.47 all the way to 0.08, and my accuracy went upwards all the way to 97.18%. So the trend is always that with accuracy, you're trying to go upwards, And with loss, you're trying to go downwards. If forever these are stagnant, if they're not moving, that means something is wrong. That means your model is not learning. If accuracy is going downwards, that means that is also a problem. If loss is going upwards, that is a problem. And somehow, once you go through this a couple of times, you'll start seeing patterns in the way it's training. So I just chose 5 epochs. However, you can run this as many times as you like, maybe 10 times, and that will train it 10 times. So you can see now it's at 1 out of 10. And the more epochs you have, somehow it can improve your accuracy. You'll get higher accuracies. However, if you train too much, then you might end up overfitting on your data. So you have to ensure you have a balance of how much you're going through your images. If you go through images too much, it's like as if you're saying, this is the whole universe of this model. Ensure this is all you know. What you want to do when you're building a model is you want to ensure that you're generalizing. So you want to generalize your data and you want to generalize all those features. You don't want to be specific that this is all that exists. You just want to get those features and say, this is what it could be. So ensure that you use enough epochs, but not too much. There is not a specific number of how many. You just have to keep trying yourself, and then you'll see it once you run the model. So this is a very simple example. This one is available from the TensorFlow website. Now we're going to do our own version. This version is the one that will use our own data set. This time we have a data set of our own, which is the orange, the fruits, the orange, banana, and apple data set. However, because we have a different way of training, we also need to find a way to get our train data, our train labels, our test data, our test labels, and so on and so forth. So there has to be a new form of splitting. So to split our data, there is a script over here called splitDataset.ipynb. And what this does is it takes your data set, you give it the ratio that you want to split, and then it will create those new folders for you. I always suggest creating a new folder set and not replacing the one that you have, so that if you want to change your ratios, you can change them later on. I'm going to call this one set C. So firstly, I need to define where my data set is. You might need to change this if you're using a different one. So this one is data sets. I'm using exactly the processed fruit data set. Later on, you can also use the augmented fruit data set to see how that impacts your accuracy. Then you have to state the subfolders. The subfolders inside of this one are apple, banana, and orange. Um, these are currently in alphabetical order, and that is how really your data is expected to be for your class names. And then your output folder, I'm calling mine set C because I have already created set A and we did set B in class. I'm just creating a new one called set C. You can name this whatever you want. You could have named this, let's say, dataset 1. That is up to you. But you have to remember what these do. I do suggest having a notebook on the side, a physical notebook that you can write what these data set mean to you, how many ratios you had for each one, and your experimentation on it. So the train ratio is how many images you want on your training side. I'm saying I want a 70% split on my training. I want a 20% split on my validation, and whatever is remaining, I want it on my taste ratio. So this will be 70%, this will be 20%, and this will be 10%. Um, when it comes to validation, this is a new thing. A validation is a form of test set that is used while you're training, and it can have many names. You can sometimes see it as val or validation or dev. It's a development set. So these are some of the keywords you might see. They all mean the same thing. With training, you might see train or training specifically, and test will be testing or just test. This function will do the splitting for you. I commonly use dev as my validation name. So you might see dev a lot. You don't really need to know much about this function. All it does is take your images and split them up. So I'm just going to run this and so play this one and play this one. So I have set A, set B, and set C. So I'm using set C. So we have a development set with apple, banana, and orange. We have a test set with the same things and a train set with the same things. So it did a split across three different folders. So now that I have all of these, what I want to do is I want to use almost the same code to be able to create a model. Now, what we're using now is something called CNN. Inside of script.ipynb, there is code that will let you use convolutional neural network to be able to train your model. So what CNN is it's a way of extracting features from an image, and different kernels, different filters will do different things. Inside of visuals, the first image convolution one, you can see that there is an image of a boot and you can almost see the pixels. If we were to take these pixels and multiply them by this filter and add all of those values, we can get a new value for this 192. So it takes 192 and all neighboring cells around them, and then it multiplies them by this filter definition. So you can see the -1 gets multiplied by 0 over here, and then it gets added to 0 multiplied by 64, and it keeps going that way. And that's how you get the new pixel value. And this is a way of creating different sort of extractions out of your images. So this is a normal image. Once it's given this specific filter, it sort of makes all of these vertical lines more prominent and gets rid of everything else as much as possible. So you can see the horizontal lines are sort of fading away. If you were to really do this again, make it more stronger, you'll start seeing that all of these horizontal lines start really going away and all the vertical lines become more and more prominent. So currently you can see these lines over here on the stairs are becoming very, very strong. And these vertical lines over here are also becoming strong. And then these horizontal lines are sort of fading away. And there's another filter, this one, that will do the opposite. So it will make the horizontal lines more prominent and the vertical lines less prominent. So this is a different set of features. So this is convolutional neural networks. In this script, there is TensorFlow, which you have already installed. There's also another package called Seaborn. Seaborn is a graphing framework. It's a bit similar like Matplotlib, but it makes the graphs more beautiful. So whenever you want to graph something, make it more beautiful for your articles or presentations, you can use Seaborn. There is an API for it, or if you want to go through the tutorial yourself, you can go through it to graph better graphs. However, for us, we're just going to use very simply to create a confusion matrix. We're also using scikit-learn at the end to be able to test our data and get some of the metrics. So I'm going to play this to ensure everything is installed. Once you get a tick, that means everything is okay. Now we're going to have our base settings. I'm going to use OS, which is the operating system libraries. The base settings is I want to go to data set and then data set C. And set C had, if I can remember, in the split, we have 70%, 20%, and 10%. So this one had 70%, 20%, 10% test. So I'm training with 70% of my data, I'm validating 20%, and I'm testing with 10%. And it will go to that base directory, and then it will finish off with my settings. Now I have something called batch size. It means that every time I go through my model and I'm training with my batch size, I want to take these many images at once and learn through it. So if let's say you're teaching a child and you're saying, I'm going to show you one image at a time so that you can learn, we're saying you have a batch size of 1. If your, let's say, student is learning with 2 images at once, you're showing them 2 things at once, that means it has a batch size of 2. That means, let's say you're holding up 2 cards of apples, like these are apples or these are oranges, learn these at once. So when you say we have a batch size of 32, it means that we have 32 of these images being kept at once, being learned at once throughout this epoch. The image size is something we can remember. This is the size of the image, the dimensions of it. So the image size will be the same for the height and the width. Now we're going to import our data set. We're not importing the library, we're just importing it normally from our folders. Remember, the values are alphabetical, so it's apple, banana, and orange. And this will be inferred automatically because you have them in a folder. So this code comes from TensorFlow itself. This is from the library. If you go to their library and scroll up and you go to load and pre-process data, specifically images, and you scroll down, you will see the same code here along with batch size. So I have combined these two to just image size because they're the same. And then your trained data set, what it does is it takes in your trained data directory. You can also just have one trained directory without a validation and then split while you're training. That is also something people do. You can set the seed for reproducibility if you want. If you want, just let it run randomly. And then you have your image size along with a batch size. So similar to this one, we have our base directory, and we're specifically saying I want this to be with the train because instead of set C, this will be our train set. And then our labels will be inferred. We're using categories. These are the categories, apple, banana, and orange. Our image size, this is image height and width, is going to be 64 by 64. Our batch size is 32. We have some shuffling. Shuffling is true. That means it will shuffle all of your images. And we're setting the seed to 42 so that we can reproduce this with the same sort of sense every time and get clear values. So we are loading our training, and then we're loading our validation, and we're also loading our testing. The only thing that's really changing here is the name of the folder. The one thing you should note is the shuffling. The shuffling helps this sort of pick up on new, let's say, patterns depending on how your images were ordered. So your images sort of should not sort of follow in the same pattern. Your first image should not always be first. Your first image should be randomized so that you can learn really, really well. Similar to the validation, you also want this to be shuffled. However, when testing, shuffling does not make a difference because you already know the results. You just set this one to false. You really do not need to shuffle your test data set. Um, Most of the times, even if you were to set this to true, it would not do anything. However, you do have a problem of memory constraints. If you have 1 million images in your test data set, shuffling a million images takes you time. So rather than wasting time in memory, you don't really need to do that. You just set this one to false. So apart from loading this, I'm going to play it. It's going to show you how many images you have split. So the first one was for our training. We have 164 images belonging to those three classes, apples, bananas, and oranges. We have 82 images also belonging to those three classes, and then 29 for testing, belonging to the same three classes, apple, banana, and orange. The next step is to define your model. So we have layers, and different layers do different things. We have talked a bit about dense layer, and now we have these two new layers. We have convolution 2D. Convolution 2D will perform your convolution processes, which will extract the features. I'm going to start off really small here and explain what these numbers mean. I'm going to do this, for example. And then we also have a max pooling 2D layer. So the new one, I guess, will be this max pooling 2D layer. What a max pooling 2D layer does is it takes the image and shrinks it in size. So you have a really large image, it will take a portion of it and then pick the largest number out of it. So for example, you have 0, 64, 48, and 192 as this one. This one will be this one, this bottom one will be this one, and this one will be this one. So it will pick the largest number out of these. For this one, 192 was largest, so we picked this one. This one was 144, this one was 255, and this one was 168. And then it will replace all those values accordingly. So this will be your continuing image. It will shrink it. And you want to do this because you're trying to go down this convolutional neural network. You start off with a lot of layers, and then they are supposed to keep getting smaller and smaller until you get your output layer. So for us, our output layer is 10. Our input layer is really, really large because once it flattens, it becomes a lot of images. So we'll start here. The first step is normalization. This is the image being divided by 255. And then the input shape is our image size, which is 64 by 64. That means that when it's flattened, this whole thing, the whole row will be 64 by 64. And then we have this 3, which is the RGB channel. So red, green, and blue. So you have these many neurons at the start. So this is a very large input. And then all of that needs to shrink down all the way to the 3, which are apple, bananas, and oranges. So I'm going to start off with 16 here. and then I have another one 32, and then 64. So I convolute here, I pull it down, shrinking the size of my image. I do it again, another convolutional layer. I pull again, another layer, and then another pooling, and then I flatten everything so everything becomes one row. Then I have 128 new nodes that I'm going to connect to. And then finally, a dense layer with 3 outputs and activation of softmax. So I'm going to play this, and it's finished. And then I'm going to click on model summary. Model summary shows me my layers. Now, you have usually a lot of layers. When you look at this, is a lot of layers. When people count layers, they'll count differently. Some people will say they have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10 layers total. However, the most common approach is to only count the most valid layers. So the valid layers are the convolution 2D layers and the dense layers. These other ones aren't really layers, they're just processes that perform something. So some people will not really count the pooling or the flattening layers. So if you're counting differently, you'll be counting 1, 2, 3, 4, 5. So you have 5 total layers. And most common, you'll see this kind of counting being done, that you have a 5-layer model. You can try counting other models. If you ever find the structure of VGG16, you'll see that it actually has 16 valid layers. But when you look at the whole structure, you'll see more layers than are actually defined. So this is layer counting. And then you also have parameters. These are the available parameters for you to train the tweaks that you're trying to make inside of all of these neurons. The more parameters you have, the longer it will take. So for example, if you have 50 million parameters, you'll see it train really, really slowly. And if you have, let's say, 50,000 parameters, then it will train really, really fast. So this is a very low parameter. It's 2 megabytes. It's not that very large. So it will train very, very quickly. Similarly, it also depends on your images. If you have a very large network and you have less images, it will also train very, very quickly. But if you have a lot of images and you have a very large network, it will train very, very, very slowly, and you need more computing power. So when you have like 1,000 images, that is known as a very small data set, and you need to create a very small, shallow model or use transfer learning to be able to create a proper model. So this is the very small model. This is if you have not enough data, you're just trying it out. If your data is not fitting very, very well, then you might want to use transfer learning. When you have 25,000 images, like between 1,000 and 25,000, then you have a medium data set. Um, then you might need a bigger model, a deeper model, but you can also use transfer learning if you want to enhance the accuracy. So when you have, let's say, VGG16 with 16 layers, that is enough to be able to train a medium-sized data set. And when you have a really, really large data set that requires larger networks, for example, you have a million images, you might want to use, let's say, ResNet 101 or like a DenseNet, I think 121 or something big with a lot of layers. However, the more layers you have, the longer it will take to train. You might see numbers of maybe 1 to 3 to 5 hours per epoch, or even 1 day of an epoch, which can consume a lot of time. So ensure that your computer actually has the memory and capacity to train your data set. I would always suggest trying out with a very small portion, like let's say 1,000 images to see if it's working. And always sort of work with a medium data set if you're working on a laptop. And then if you have a really large data set, then work online on, let's say, a server so that you can utilize their resources. Finally, once you have looked at the model structure, you can compile it. You have optimizers. There's an optimizer called Adam that lets you specify the learning rate. The learning rate is how slowly you want to go down the descent. So similarly, you can say that we have, let me go to this one. Let's say this is a lake, for example, and you're trying to descend this lake to get to the bottom of this lake. Your descent optimizer, Adam, for example, lets you descend certain steps. So you can say, I want to descend 0.01 steps every time. For every epoch, so I'm going to descend a little bit, and then a little bit, and then a little bit, and it will keep descending that way until it gets to the bottom. If you have a really big value, it will go very, very sharply. So it might go like pop, top, and then all the way to the bottom. It might actually not work very, very well. It might even go wrong. It might go in the wrong direction. The lower your learning rate is, it will go smoothly down. However, it will take more time. So the lower it is, when you go from 0.0001, for example, it will take more time, but it will be more accurate. But if you have a larger number, it will take less time, but then it will not be very, very accurate. However, you also want to balance your learning rate. You don't want to go really low. That may really be bad for your model. It might overfit. So you want to sort of range somewhere. I will always suggest starting at 0.001, which sometimes you'll see as 1e to the power minus 3, something like this. And then either add more zeros or tweak this number a little bit so that you can sort of figure out the proper learning rate for your model. And then we have the loss. This is for classification. And currently we just have a metrics of accuracy for this. So I'm going to play this as well. And then I'm going to train my model. It's almost the same as the other code. We have our training data. We have our epochs, which are currently 10. And then we have our validation. Our validation is to test while we're training. I'm going to play this so that we can see what happens. Okay, so it went from 1 to 10, and you can see it went from 0.44, which is 44.72%, all the way to 89.75. You can see it had a glitch here. It got to 91% and then started going downwards. If these values are not too far apart, then it's okay. But if it's going down as a trend, that means something is going wrong. Our loss start off at 1 and it's going down all the way to 0.35. So that means it's going okay. So I'm just going to keep it at 10 for now and continue. Next step is to save your model. I'm going to call this custom CNN, and I'm going to play this. This will save your model. And then I want to evaluate it and see what it did. So take my history, the one I've trained with, and graph what happened while I was training. So you can see with the training, it started off it's at 0.4 something. It went down a little bit and then it started going really, really up really, really quickly. And then similarly to this one, it's also going in that trend. Because it kind of shot up really, really quickly with this one, this is a sense of overfitting. However, you cannot be sure yet until you train all the way. It's just that we do not have enough epochs to train. With loss, this is going downwards. You can see that it is sort of going down at the same time. So it might be a little bit overfitting, but we're not so sure because the gap is not that big. So we might just need to train more and see what happens. What you need to watch out for is this concept of overfitting and underfitting. If this blue line shoots up very quickly, but the orange line is not shooting up very quickly, that is overfitting. I'm going to write this down here. The line colors might be different depending on your settings, but for me, so the blue color, the training accuracy. So if this training is going too fast, if it is going too quickly, but the orange line is not going at the same pace, then this is known as overfitting. And then similarly, we can say if the blue color is going on really slowly, as well as the orange line, both of them being really slowly, then we can say these are underfitting. And then if they're going at the same pace, and it might not be really always at the same pace, but really, really close to each other. If they're going at the same pace and they are getting really, really high, then we're saying they're fit, that is training correctly. So do watch out for these patterns in the graph. Similarly, you just have to watch out for the same thing with loss. If in the blue color, the loss is going sharply down, but the orange line is not following sharply the same way, then it is overfitting and similarly with the rest. So this is the concept of overfitting and underfitting. You might also see it in some of the other graphs going forward. Then what we're going to do is predict. So we have some other metrics like precision, recall, and F1 score, and these sort of show you how precise your model is being when it's predicting, how sensitive it is to new images. Like if is it really predicting it correctly as what you said in your accuracy, and so on and so forth. So there are many metrics. I think there will be an extra video just to explain these metrics whole, because they will also be used for machine learning, the third week's course. So I'm going to play this. And then when I'm training, even though I got an accuracy of 89.75% at the end of my 10th epoch, when I'm testing, I only get a precision of 83, which is close to the accuracy itself. So we're saying it's only 83.6% precise. And its sensitivity is also 83.3, and the F1 score is 82.4. Lastly, we have this confusion matrix. The confusion matrix, it describes how confused your model is. And we look at this as a block figure, as a diagram, as a matrix. So we're saying that this diagonal line, this is when everything is going correctly. And the values at the bottom means something is going wrong. Also, the values at the top mean something is going wrong. So let me close these so I can open the confusion matrix. So in the confusion matrix image over here, we have these values. This is a 2x2 grid. This one is a 3x3 grid. So in this example, we'll just have this, for example. In a 2x2 grid, we're trying to say that the diagonal line represents all the correct values. So we're saying if something is positive, then this first one will be that it was positively positive. So it is a true positive. It is correct. And if it was a negative and we also got a negative, that means it's a true negative. That means it was wrong and we said it was wrong. The problems arise when you're saying something is correct. The model is saying something is correct, but it's actually wrong, or that something is wrong, but it's actually not wrong. So these are the false negatives, and they fall on this side of the matrix, and the false positives are this on this edge. So false positive is an incorrect yes, and a false negative is an incorrect no. And all of the other metrics fall in this sense. It will take, let's say, the true positive divided by the true positive plus the false negative, and that'll be the sensitivity, and you'll have the specificity and the accuracy and the precision and so on and so forth. So these describe different things on your model, and they can sort of help you to realize if your model is overfitting or underfitting. So in this sense, we're trying to say that we had an apple and the model predicted 6 apples correctly. We had bananas, 9 of them were predicted correctly. And we had oranges, and 9 of them were predicted correctly. However, for our false positives, we're saying we were given a value, and then it said that it was a banana, even though it's supposed to be an apple. And for false negatives, we had 3 of them, and it said they were apples, even though they were bananas. And then one of them was also an orange, but it said it was an apple. So these are your false negatives, and these are your false positives. So this is the diagram. You can go through this so you can understand it. Even though this is 2x2, it might be different for you depending on how many classes you have. You may have 5 classes, so this will be a 5x5 grid. Finally, because we already exported our model, my model was called custom CNN. I want to use this to test out if my model is predicting correctly. So I'm going to call in the model, and I'm also going to call in a random image. There is a folder of images you can use to test. I'm going to try out banana, for example, .png just to see what happens. You have to use the same settings. I had 64 as my image size. If you do replace a different number, you will see this give you errors. I'm going to try this once without changing this number, and then once if I change it. And then it will load the model and give me a prediction. When I play this, it gives me a 99% accuracy that this is a banana. If I was to change this number to 128 and I play this, you'll see an error, and it tells you that the input does not expect 128 by 28. because you started it off as 64 by 64 when you declared the model structure right here. You're saying, I want to start off with 64 by 64 as my input shape, as my image size. So when you're predicting, you also have to use the same settings as you use for training and validation and testing. Everything has to be the same throughout. So this has to be 64. So this is a banana. I'm gonna try another image, orange.jpg, and that gives me a banana. That means something went wrong. This is not very, very accurate. And then I'm gonna try another image. Let me try orange 30. I'm gonna play. This one gives me an orange with 93% accuracy. I think we also have another one called banana test. Let's try that one. When we play this, we also get this as banana. So we saw that there was one mistake, and we can actually prove this was the mistake that we were trying to figure out. And somehow you may not be happy with your accuracy because it might be really, really low, and you want to maybe improve it. To improve your model's accuracy, there are many, many things you can do. The first thing is to use augmentation. We already have an augmented fruit data set. Perhaps rather than using this set, I can create a new set. I can say I want to split from a different data set. So this is going to be augmented data set. And I want to keep the same ratios, but it's going to be set D. I'm going to play this. I'm going to play this. And then in my script, rather than using set C, I'm going to use set D. So that might improve my accuracy. So once you're here and you've changed stuff, especially at the top or even at the bottom, it is wrong to just play where you are. For example, let's say I've already changed my set D. You should not just go and retrain this cell. You're supposed to run everything again. So the best way is to just click this run all button and it will run all of your code from top to bottom. Or you can click every single one at a time so that you can see the process. So I'm going to click run all. So now we have more images for our training. Okay. It's now training. We're getting better accuracy. The loss is also going down a little bit better. I'm going to resave it as the same one. Yes. I'm going to play it. You're going to see like it's going a little bit more smoothly. It's trying to go more smoothly. And then finally, you also have a different sort of result over here. So we have more images this time. We had 18 apples, they were all correct. We had 18 apples that were correct. Two of them were false positives. One of them was false negative. 17 of them were correct, and then two of them were false negatives. So this was wrong. So it's getting a little bit better. Let's see if it can predict these correctly. So we have a banana. That is correct. Let's see another one. Let's see this banana. This one is also correct. We have an orange. This is now okay. And we have orange 30. And this is also okay. So all four images are okay. That means our model is improving and it's getting better. So one of the ways to improve your accuracy or your model itself is to use augmentation. Another way is to decrease or increase the learning rate. So I could have chosen a smaller learning rate just to see if that improves my accuracy, if it maybe hits 99%. So I'm going to lower this by 10 here just to see if it makes a difference. Remember, you have to run all from the beginning. Okay, so this time it went to 74%. However, you can see it's sort of starting to kind of go together. Also, the loss is smoothly going down. So maybe the trend is okay. Maybe another way would be just to increase my epochs. Let's say I want to go for 50 epochs. Let's see what this does. So remember, we run all. So let's see what happens when we run 50 epochs. So it's currently at 70. It's getting to 90%. You can sort of see that it's kind of stuck at this 93, 94%. It's not going that much higher. So that means we're training way too much with the same setting. And you can see that it's just sort of squiggling down, even though the loss is sort of going really, really smoothly, the training is not going so well. So we know that now the loss is way too much. So we need to remove it and go upwards. So let's say I'm going to use 0.01, and then we're going to run all just to see if there's a difference. So I'm going to let this run with the 50 epochs, and then we can see later on what happens. But this is all about training. You're trying different things. You're trying, it's almost like trial and error to see what works for your data. Different data requires different models. You might want to change your model size. You might want to use a very strong model, one that has already been tested over and over again. So you might use a VGG16 model here rather than your own custom model. Another thing, you might want to change your image size. Image size is a little bit controversial. The bigger it is, it does not mean that your model will perform better. It might not, it might just be the same. These numbers will range from like 32 all the way to 512. Um, any number in here is valid. You can choose any number, honestly, that you like. However, it does require more memory. 32 is very common because it does not utilize so much RAM. You can also use 64, which is a very safe number as well. But when you get to numbers like 128, you'll start seeing your model train really, really slowly and taking up more time. However, it might pick up more features. So if you have a little bit of space, a little bit of CPU power, try the larger image sizes to see if it improves your model quality. When you get to really large sizes like 224 and 256, you might need assistance with like GPU support so that it is able to multiply all of these pixels at once. It is very rare for a computer to be able to, a normal computer to train 512. You might see it lag, almost not respond at all. I would never suggest on a normal PC to run 512 image sizes. It might crash your application, might crash VS Code. So try and stay away from these large sizes as much as possible. Stick with the small ones until you're used to the big ones. Um, Apart from that, you can also change the batch size. This has an impact on your training. You can start off really small, and if it allows, try bigger batch sizes to see if that affects your accuracy. Another way is also to remove the seed and see if it impacts your training. Apart from that, I guess the biggest part is always your architecture. Your architecture defines everything. You can try out different filter sizes here. For example, I could have tried 64 and 64 just to see if that makes an impact on my model's accuracy. So I have trained for 50. I can see that it got a lot better. It now got to 99%. Let me check. The accuracy is a little bit still shaky, but it's a lot better than last time. Let me replay with my current new settings. I'm going to run all one more time, and that will be the last time we run. Apart from that, this is how we train models with deep learning. You just have to try out new things over and over and over again until it works for you, until you get a really, really good accuracy. So this time around when it was running, it only had one misclassification for banana, but this is because we don't have too many images. So it's okay right now. And all of our images are from the same distribution, they're from the same data set. For some people, they do choose to have a different test set that will come from a whole different data set itself. I would suggest always sticking to the same distribution first while you're making the model, and then later on using another test set from a different distribution, a different source to be able to test if that works as well. So this time around, it tested really, really poorly. It's always about trying new stuff. So let me see. I think this has changed. this one changed to 32. So we have to change this to 32. So most of the time when you're making changes, ensure the changes are consistent throughout your code. So this one now has to be 32 because I changed that side to 32. So try out different things, try out different test splits, try out with more augmentation if it will help. Um, Try out different combinations of these layers. You can find these layers on TensorFlow's website. When you go to TensorFlow and you search, you can search for layers and it will show you the list of all the available layers on TensorFlow, as well as the documentation. So you have activation layers, you'll have the pooling layers, you have the convolution layers, and so on and so forth, and the dense layers and so on. So go through them, try and read them, see what they do, so on and so forth. So this is the lecture for this week.